for the introductions, for having me here today. It's always been a pleasure talking about the latest and greatest in silicon photonics here at the ECOC. This year, obviously, it's a little different compared to the other years. Hopefully, we're getting back to normal soon. Yeah, so obviously I'm trying to address the optical communication and silicon photonics market more from an industrial perspective and from a user perspective. I'm glad to see the lineup in the talks of speakers here. Lars was talking greatly about and demonstrating the technical capabilities, but also the service capabilities of IHB, where we very much built on. It's been a great journey together for the last, I don't know, 15, 16, 17 years. But I really wanted to focus on co-packaging and what it means for the optical communication market and what impact it has on the industry as such, and how Sicoya can contribute to the overall success of that technology. All right, so just at a glance, very quickly, I think Sicoya is pretty much an established brand, which is for those who haven't seen it. So we've been officially founded back in 2015, but as I said, we started research here on the silicon photonics platform back in 2006 or so. There is a monolithically integrated technology platform that we developed together with our partner. And our focus was on industrializing products, bringing them into the market and actually shipping products. So we're very much focusing on the transceiver market and for both datacom, but also for 5G telecom applications. We have some activities in the automotive and also in the sensor space. Despite well, we should say, except the foundry as such, so we do not own any chip-level manufacturing technologies in-house, but what we do own is all the rest of the value chain. So everything from the package level from the engine level to the final product, to the transceiver level, we own in-house, and that's one of the key competence and capability that we bring to the market. The core competence obviously is designing chip, and I would say, no offense, Lars, but some of our performance metrics in the chips in terms of volts per centimeter or losses are better than what you presented. So I don't need to spend a lot of time with technology because that has been demonstrated. So as we said, we're monolithically integrating the optics and the electronics. So the optics in the local SOI, the electronics, and then in the bulk. It's quite a state-of-the-art by CMOS process. So we are not making any compromises both on the electronics or on the optics, which is of course important to come up with competitive products. And it's not the end of the journey. We continue to develop and to come up with next generation processes to stay competitive, not just to be competitive, but to stay competitive also in the future. Of course, what we see from an industrial perspective is that it creates a lot of advantages in terms of cost. So you have fewer assembly steps, you have margin improvements, you have lower power, all of that. The technology, using this as a tool to be more competitive and better products compared to other solutions. So here's a couple of pictures of products that we developed in the last couple of years. So all the range from onboard optical transceivers or onboard optics to 28 gig industrial temperature, 10-kilometer transceivers used in 5G telecom, 100G product range in the data center, but also 400 gig transceivers, both parallel versions, but also WDM-FO4 type versions. All of them rely on monolithically integrated silicon photonics engines and chips that you see here on the bottom. And for those who are interested, so we do business on all different levels, so both on the chip level, on the engine level. Sometimes we help companies with designing even pedal cards or PCB boards, but we're also selling transceivers. All right, so moving more into the main topic of the talk, which is co-package optics. So I came across recently this famous chart that I've used a lot, 10 or 15 years ago. I thought it's worth sharing it again because it shows nicely that we as an industry are moving on a trajectory for, like the last 40 years. So optics has been introduced in the 80s for long-haul telecom, used in metro networks, has been used to connect data centers with each other, and now it's in the data center. It's even went to the rack already. We're using AOCs and transceivers for connecting racks and pods, but we're still using a lot of copper inside the racks. Copper traces, PCB traces, and I'm still using a lot of copper for connecting servers, for example, with the switch. And moving to CPO, actually, so co-package optics actually represents the next major step on that trajectory here. And it will have a great impact on the ecosystem. And what always happened over the last 40 years that once you make a step further on the trajectory, it came along with cost reduction per gigabit, and it came along with great energy reduction per bit. Right? And we expect the same thing to happen once we move to co-package optics. Now, there's another fairly well-known representation of the same story. So we had started on the switch, at least, with using pluggable transceivers at the front plate. The initial, transceivers at 10 gig had no, well, at least on the SFP level. So some generations later, at the 10 gig level, there was no CDR integrated. And then we added CDRs on 25 gig, and then at 50 gig, we added midboard or onboard additional CDRs between the switch and the transceiver. The laser always been obviously in the transceiver. And then some companies use embedded optical modules to reduce further the distance between the switch and the optics. And now with CPO, it's time to bring the optics to the package level. And at least the first generation, we're expecting to be, like a miniaturized version of a transceiver that we bring to the package. We call this a tile. The CDR or the DSP is going to be integrated in the package or in the tile. And what we're expecting still to have pluggable modules at the front plate, but only that those modules at the front plate are having lasers and potentially other functionalities like MUXes and DMUX. And then the ultimate, maybe not the ultimate solution, but then the next step is to, similar to what we did at 10 gig, to eliminate the DSP, the CDR from the tile, and move even further or closer the optics to the ASIC, to the switch, for example. And this would further eliminate power and eliminate copper. So this is how we see this. Now, how do we achieve power reduction? So we achieve power reduction basically, for example, by having remote laser sources at the front plate. So there's a much better place for lasers. You can cool it better. The lasers stay cooler. So you get more optical power per electrical power. Right? So it's more efficient. Lasers are more efficient. And we're eliminating copper traces, so we need less, less equalization. We need less voltage swings. We less pre-emphasis on the electrical side, and those are the two things that fundamentally change the power envelope of the solution. And of course, we're making technology advances. We go from 7 nanometer to 5 nanometer, and make advancements on the silicon photonics side, but those advancements we could also utilize in the transceivers. So this we should not, associate with CPO alone. So the CPO is an architectural change, and with that comes cost reduction, power reduction. So this is the summary of the electrical channels. So at 100 gig, we started with 25 gig, maxing this to 100. 400 gig is 2 by 50 or 8 by 50, actually 2 to 400 or 2 by 50 to 100. At 800 gig, we're moving to 100 gig SerDes and still have retimers. And CPO, at least the first generation of CPOs, are most likely going to use the same approach, 100 gig in, 100 gig out with the retimer and the tile. But then again, one of the targets is to eliminate the DSP and move to an unretimed interface between the ASIC and the optics. So now, we're not a system company, but we came up with this chart to illustrate what it means for switches. So we have several generations of switches here, utilize the same architecture with the front plate pluggable modules. Currently introducing 25T switches, and all of them had either 32 modules or 64 modules. So the 6.4 tera was mostly a 2 RU design with 2 rows, or even 4 rows with 64 QSFP modules. So 2 RUs switch designs seem in general to be less attractive in the market than 1 RU designs, which is no surprise, as offer better density. And so now at 50T, we have basically 3 different options. You could use 64 modules with 100 gig SerDes inputs, or you could use 32 transceivers with 1.6 T each. So that would require 200 gig SerDes. Or you could switch over to CPO, which in one implementation would be using 100 gig SerDes and have a tile IO capacity of 3.2 T. So which of those are going to be introduced first, and what are the risks associated? I mean, many companies have different opinions here. Some say it's easier to introduce 200 gig SerDes first. Some others say introducing CPO with 100 gig SerDes is easier to do that. As a company, Sicoya, we just need to make sure that we have the right components to enable all of these different solutions depending on the customer requirements. So we're talking a lot in the co-packaging space here around technology. So there's silicon photonics is pretty much the baseline. There's not a lot of debate here, even though some companies say we should use VCSELs also. But most of the discussions that we are hearing are around whether we have remote laser sources at the front plate, or should we integrate the laser, quantum dot laser or quantum well lasers, comp lasers possibly, mass senders versus rings. How do we distribute the lambdas on the different fibers, with one lambda per fiber or multiple lambdas per fiber. And then, of course, there's multiple system specs. But I just want to emphasize one thing. Whatever we do, at the end of the day, we need an ecosystem and need to make architectural choices that allows the ecosystem to innovate and make technology generations over several switch generations. So it's not the target to come up with one 50T switch. The target is to come up with a new architecture that can utilize over many different upcoming generations. And the key of that is.
Ich konnte den Lautsprecher leider nicht finden.
Sorry for that. So one of that important thing is that we need to come up with value products in terms of performance and reliability at pretty obvious cost of ownership, which includes the serviceability. And to guarantee a solid supply chain. So especially small startups and small companies say they have large innovations. Question mark is always how much value does it really create for the customer? What is the cost may not be as good as they claim initially because they don't have scale. And then of course the supply chain, if you're the only company having something, that doesn't really help the customer eventually too much. So you always need to make choices. And having a concept that allows all the different things and to innovate is required. Now, this is a possible way of doing it. So you have a CPO in the middle, and our approach is really trying to, it's probably the wrong word, but kind of disaggregating the transceiver. So basically stripping it down into the individual pieces, into the individual functions of the transceiver. So concentrate the CPO package on the IOs. And all the rest of the functions, for example, the laser, but possibly also muxes, demuxes, other functions, to put this at the front plate. And the reason is that silicon inherently is very reliable. We know this for many years and decades. whereas some of the other components may just inherently have less reliable. So no offense to anyone here, but it's just what we're seeing. And connectors, for example, is a good example. So connectors are not inherently as reliable as silicon chips. So all those things have to go to the front plate, because this is where things are serviceable, where you can actually touch them, replace them if they fail. So in this example here, you have 32 slots. 16, for example, could be used for the laser sources, and the other 16 just for fiber feed through, muxes, demuxes, and other functions that you want to put there. And the nice thing about this concept is that actually by disaggregating the functions of a transceiver, the individual companies can innovate on these individual levels. So laser companies can innovate on the laser level, can come up with tunable lasers or whatever. Power tuning, mux, demux companies can innovate on that level, and silicon companies can innovate on the silicon level. So that's, I think, a nice concept that enables an ecosystem that would survive over many generations. So this is just some graphical interpretation and representations as how this could possibly look. So we have a W2M version where you have a laser source with multiple lambdas and an I/O module which has mux demux functionality, or you can have parallel versions where the laser source only has one lambda but on different fibers. And all of those go to the tile, and then on the I/O side, you would only need possibly breakouts or mechanical features for feeding through the fibers from the inside of the box to the outside world. And we may need a new MSA for that, possibly. Now, here's one example, courtesy of Sumitomo Electric. This shows a laser module. It has an electrical interface. It has an optical interface, both at this, on one side of the transceivers. That's something I guess we need to get used to as an industry, that the electrical side and the optical side is both at the same side of the module, and it's pointing inside the box. Now, Sicoya, what is it? What we do? We do silicon. Here's our 400 engine and chip. It has great transmitter performance. The modulator is designed to have currently 35 gigahertz of bandwidth, and if you turn on the driver, which is monolithically integrated in the chip, you're getting 50 gigahertz of bandwidth. And just by fine-tuning some of the settings, we could even have higher bandwidth. And so we feel like we're ready for 200 gig. We're obviously hoping to utilize 100 gig as much as possible, but if customers require that, we could also support 200 gig. It's very much a linear device, so whatever you put in terms of modulation format or in terms of data rate, the silicon is just passing it through from the electrical side to the optic side, and both on the transmit end, but also on the receive side. So whatever the receiver receives, it passes it over to the DSP. So those parts could be used for prototypes, for CPO prototypes. And one of our next steps is to scale this up to 32 channels, so going from 4 channels to 32. Now I just want to spend just a few seconds on the advantage of bringing optics closer to the SerDes, to the ASIC. Here's an example where if you would assume 50 millimeters or 5 centimeters of distance between the DSP and the ASIC, and if you could say you could go to 2 centimeters. Then you have 40 dB of improvement. And so you need less equalization, etc., which drives the power. And then overall, if you do an estimate, if you do a calculation with a tiled version, so with the DSP in the tile, it come up with potentially 900 watts of power and 9 by 9 centimeter substrate. And if you would eliminate the DSP, you could say go to 600 watts and on a 5 by 5 centimeter substrate. So it's quite a bit of improvement. It's still ahead of us, but probably the one that you see on the left is probably the first generation, and still large challenges that comes with it. And one challenge is to get it manufactured, actually. So it's not just designing it to PowerPoint, but to actually do it is a different story. The advantage of pluggable transceivers is actually that you can do, and utilize your manufacturing processes that you have in-house. So we at Sicoya, we use OSATs on the silicon level. On the engine level, we do both contract manufacturers and internal processes, and on the same on the module side. Now, the CPOs, we're expecting to go mostly to OSAT. So you need to enable external OSATs or ODMs. And the two or the minimum two processes that they have to do is the EO wafer test, so electro-optical testing at the wafer level and putting fibers to the device. And if you take a look at those two particular processes, I think we at Sicoya made, with partners, a great progress on the wafer level testing. So this is our second generation wafer level test card. It's absolutely stunning how great it performs. It's touch-free, so there are no fibers touching the silicon. It has the same accuracy just as the electrical probe, so we don't need any optical fine alignment or anything. It's super fast, a couple of seconds for each device. No optical alignment, as I said, and very good accuracy and reproducibility. So we see just here one example of the last, 40,000 or so devices. On the fiber side, it's a little different. So we're moving fibers around in the machine, and given the glue and the curing time and material handling, it's just much less efficient. And so if you take a look at the numbers here, this is cycle time versus process time. The wafer level test is very efficient, very fast, very efficient. The optics is just adding a little bit of extra time, and the efficiency measured as the difference between process time and cycle time goes from 90% to 70%. So still taking a hit here, but it's still reasonable. But then if you look in comparison to the fiber alignment is only 25% of its time. It's doing what it's supposed to do, which is doing the alignment. And the rest of the time, we're just waiting for glue to cure or moving material around. So there's still some R&D needed to make the fiber alignment, more efficient. But the rest, I would say, is OSAT ready, if we would take this as a word. All right. So I think I used up probably more of my time and some of the time that Lars has given me. So I skipped the summary, and thank you for your attention, and I turn it back to Marie. Thank you.
Thank you very much, Sven, for this very nice talk. I'd like once again to invite attendees to ask any questions either in the chat or in the Q&A if you wish. And I have I guess, very simple question to ask Sven, which is, historically, increasing the baud rate or the data rate has always been the best way to realize cost savings. Do you see that continuing? Do you see it slowing down? Will it go on?
Well, I mean, in the industry, we are discussing already moving from 100 gig SerDes to 200 gig, and I think this is going to come. I think we have also an increasing discussion around modulation formats. So we moved from NRZ to PAM4. The industry has not decided yet as to what we do at the 200 gig. So yes, on the bit rate, no question. So at the bit rate level, no question, we move ahead and increase the bit rate. On the baud rate, I think at some point we start to see a settling, and probably move the overall discussion more into the modulation format, so trying to put more bits or more symbols into a bit. I should also say that the industry has utilized a lot on or invested heavily into 100 gig, is still investing, and I think 100 gig is a very good baseline for ASICs, for optics, for packaging technologies, for PCB technology and substrate technology. And I would say that the 100 gig ecosystem will survive and stay very, very promising and stay in business for a long time.
Okay, thank you very much. I don't see any other questions. I was going to ask one more, which was you mentioned the scaling to 32 channels. On what sort of timescale do you see this happening?
We typically have a turnaround time of, say 12 to 18 months. So from, making the design changes, doing tape outs, getting them back, testing them, releasing them, qualifying them. So this is a 12, 18 month time lead time and or overall turnaround time, and this is what we plan.
Oh, I do see a comment actually that there are 3 questions on the Q&A, but for some reason it's not coming up in my box, which is really frustrating. Sven, I don't know whether you can bring up the Q&A and see if there's anything there that you can read.
Yeah, I currently have some issues here on my side. I can't even see my mouse, not to speak of Q&A box. Oh, here we go.
Maybe at the bottom of your window.
Okay, I see something. What are the prospects of adding more lasers in a single pluggable transceivers in terms of power, cost, and packaging? For example, extending the 4 optical engines to 8 to support 800 gig and beyond. That's one of the last questions here. So on the laser side in general, so we have been investing a lot and trying to, at the 100 gig level, we have 1 laser for 4 channels. At the 400 gig level, we have 1 channel, so 1 laser for 2 channels. So the split ratio went from 1 to 4 to 1 to 2. And we obviously don't, that has been a challenge. So at least we managed, even though there is more than 6 dB more power needed, we managed just to decrease the split ratio by 3 dB. So we've done a lot of work to make that more efficient, but we need to do more work to be more efficient at 800 gig and 400 gig. So yeah, optical lasers with more optical power is one requirement. But we're also doing a lot of innovations and tricks on the technology level to allow more optical power to go into the silicon. Also silicon at some point, silicon waveguides at some point start to become nonlinear, similar effects like what you have in the fiber. And that is one technical challenge where we are innovating and working on technology. So I don't know if this is addressing the question directly, but this is what I can say. So there is one other question. I don't know. Do we still have time for more question, or do you need a guide?
Well, if you could answer it quickly, then yes. In a way, it transpires that we have a slight mistake in the timetable, which will compensate for the late start. So if you wish to answer it and you can do it in a minute, that would be great.
Okay, so there's one other. At 15 picojoule per bit energy efficiency, you would need 800 watt CPO. DSP SerDes OE power for a 51T switch. So, okay, that's 800. I think I said 900 or so. It's close. How is that going to fit in a switch power budget? Today, electrical SerDes for VSR are around 5 picojoule per bit. Yeah, I mean, I think this is a question around thermal design and how switches are designed. And obviously, Sicoya is not a switch company or a system company, so probably it's a little bit outside the scope of my expertise here. But I think there are very good concepts, and there's a whole industry of that works on improving on the thermal design, materials, thermal interface material, heatsink designs, liquid cooling. There's all sorts of innovations going on the thermal design, and it's one of the key enablers for making CPO happen.
Okay, thank you very much, Sven, for taking care of those Q&A kind of in a self-service way. There is one additional question in the chat, but rather than address it now, if you can take a look and maybe answer it online, that would be great, in the interest of just moving the session forward. So I'd like to thank you again, and on behalf of everyone